So in this video, we're going to move into section 3.2 of the text, which is going to deal with the concept of free body diagrams and also consider the techniques that are used to model some common forces that will show up throughout the remainder of the text. So let's begin by talking about free body diagrams. So free body diagrams are nothing more than a way to visualize all the different forces that are acting upon a particle. And of course, thinking back to our last video, these things aren't actual particles. They're physical bodies with finite dimensions. It just so happens that the loading conditions in a particular scenario, the lines of actions of the various forces acting upon it, all go through a common point. So since we have a concurrent force system, we can model that actual body as just a particle. So when we're looking at a free body diagram, what kind of forces should we expect to see? Well, we're going to see forces associated with actual applied or loading forces. So say, for example, I have my Subway cup here and I push upon it. I might see a force associated with the actual contact of my hand to the cup. In addition, I would see some forces associated with the support structures acting on the body. In this case, that would be the desk upon which it's sitting. I would see a normal force corresponding to the contact force that the desk exerts on the cup. In addition, for all of these, even though we're modeling these as particles and we're ignoring their physical dimensions, we're not ignoring their mass, typically, unless we're told to, which means that we're going to see a weight vector corresponding to the gravitational force that the Earth exerts on each particle due to its mass. When we actually show those arrows on our free body diagram, we want to make sure that we know that forces are defined by three parameters: their magnitudes, their directions, and their kind of point of application. Since it's a particle model, we don't need to worry too much about the point of application. They're all going to be applied to the particle. However, we do want to accurately reflect on our diagram the magnitude and direction information whenever we're given it, because it will kind of show us what quantities we're actually trying to solve for when we analyze our free body diagram, and whether or not we can, whether we actually have a situation that's known as statically determinate, where we have enough free equations that we can write in order to solve for the various quantities of interest that we need to determine. So why do you actually call it a free body diagram? Well, if I were to just take a snapshot of this cup, its free body diagram wouldn't show any of the physical actual contacts, actual forces acting upon it. So say I pushed it a little bit to the left and a little bit to the right, and it's in equilibrium. I'm not going to show my hand pushing it this way. I'm not going to show the other hand pushing it this way. I'm not going to show the desk actually exerting that contact force in the vertical direction. I'm going to separate it from all the physical things that are exerting forces upon it, and I'm actually just going to show the effect of those forces by individual arrows. So that's free body in the sense that you're removing the body that you're trying to analyze from all the physical things it touches that are actually exerting the forces on it, and you're just representing the effect of those contact by the forces. So when we have free body diagrams in Chapter 3, they're going to be incredibly boring. They're just going to be a bunch of arrows acting on a particular particle. So as I mentioned, we are going to spend a little more time in this video kind of describing the common forces that we will see associated with various support structures throughout both this text in statics along with the next semester in dynamics for those of you that are going to move through. And the first is an idea of a spring. And I'm not going to say too much about this because I know that we all understand the basics of this from physics. But remember, if we have a linear elastic spring and we actually displace it, there's going to be a restoring force, which is going to be proportional to its displacement. And that constant of proportionality K, which is known as the spring constant, is nothing more than a measure of the stiffness. So just so we all know some notation that is used in the text, they're going to use the distance measurement L naught as kind of the, I guess I would call it the natural length of the spring or the steady state length of the spring. So what that means is if there were no forces exerting on the spring, that's how long it would be. So if you notice in this scenario, what has happened is someone has exerted a force and they pulled the spring down. They've stretched it. And that additional distance that the spring now is, its additional length from that kind of base or unloaded length, L naught, that's actually called its displacement. This is plus S. And this is the actual quantity that's used to determine what the restoring force would be. So someone had to exert a force to pull it down. And when they pulled it down that amount, this force is, the spring, I should say, is equally trying to exert a restoring force pulling up proportional to this displacement, Ks, that's trying to restore the equilibrium length. So that part of what the confusing thing is of this diagram from the book, they're showing the force pulling down that was necessary to displace by delta plus S. When that is displaced, there's going to be a restoring force acting in the up direction on whatever body is pulling this thing down that's going to try to restore that equilibrium length. In a similar fashion, if I compress a spring and I actually shorten its equilibrium length by delta S, there's going to be a restoring force acting in the opposite direction, trying to restore that natural length. So just always just kind of play around a little bit, draw some little diagrams, make sure you can see, okay, if I have a displacement, if it's stretched, the restoring force is trying to make it back to its original length. trying to make it shorter. If I compress it, the restoring force is trying to pull it back and make it its original length or make it longer. And the magnitude of that restoring force is proportional to the actual displacement, which is the change from the unloaded length, not the total length of the spring. So what about forces actually exerted by cables? So we're always going to assume that our cables are fixed length, meaning that they can't stretch or compress, and that they are of negligible weight. In addition, we're going to assume that when a cable exerts a force on a body, that it can only pull on the body. And what that means is it can only support tension and not compression. So if I were to tie a string to this cup and actually hold it in the air, if you think about if this were held in the air by a string, the force that the string is exerting on the cup is in the upward direction. By Newton's third law, that would mean if the string is here, the cup is actually pulling it in the downward direction. So the cable itself is in tension, right? And that's all cables can be. You can't compress an actual piece of rope, right, in general, because what you would find is it just doesn't have the physical ability to withstand that compression. So this is what this is going to allow us to do, is always to know the direct sense of the forces exerted by cables. Another thing you need to know is if a cable were to pass around a pulley, the tension at any point in the cable, we're going to assume that it's the same. That's what's going to allow it to stay together. In addition, when we have a body resting on a surface, we saw this figure kind of at the beginning, kind of justifying the particle model of this wheel in this case. Whenever a body rests along a surface, assuming we're ignoring the presence of friction, which we'll talk about a little bit later in this course, the force that is exerted by the supporting surface on the body is always going to be perpendicular to the point of contact, and that is called the normal force in this case. So if a body is resting along an incline, which is elevated by 30 degrees, the normal force that the surface exerts on the body is also going to be shifted by 30 degrees, as we mentioned earlier, relative to the vertical. So in terms of how to draw a free body diagram, I hate to actually show these rules because it's kind of just one of these things you have to see. And that's how we're going to close this initial lecture of the week, is giving you some practice in my lab, actually doing it using the software. But you want to take the body of interest and remove it from its surroundings. The hard part is actually determining what the body of interest is. When you do the first couple problems, the book actually tells you, hey, draw a free body diagram at this point. But in general, you choose the point such that your free body diagram has an unknown quantity that you want to solve for. Once you've kind of removed the object from its surroundings, you want to identify all the forces that are acting upon it. Generally, make sure you have all three categories: all the applied forces, the weight of the body, along with the forces exerted by any support structures. Could be cables, could be strings, could be contacts. After that, draw a vector corresponding to each of those forces. If you have the weight, we're always going to just assume it acts in the minus y direction since it's a particle. I mean, technically it's coming from the center of mass, but remember, we're always going to assume that all forces are concurrent, which lets us use the particle model. So for most bodies, if you know their mass, you can compute their weight. That will allow you to know the magnitude and direction of that weight force. If you have a support force, do whatever is appropriate for the particular type of support structure that you're dealing with, whether it's a cable, a spring, or so on or so forth. So both cables and springs, the direction of those forces is directed along the actual geometry of the spring or cable itself. You may or may not know the magnitude in each case. For a spring, the magnitude would be proportional to the displacement, as we mentioned. And if we're dealing with a 2D problem, which is what we're going to be dealing with in section 3.3 when we move on in the actual lecture we'll be doing on Thursday, what we'll find is we have the capability to solve for two unknowns within our free body diagram. So we'll call a problem statically determinate if in our free body diagram there are only two quantities that we don't know, because we're going to be able to write two equilibrium equations. So what I'd like you to do to kind of finish this out is to go to, even though this week technically only chapter 2 homework is due, I also put a chapter 3 homework in my lab that is a bit of a tutorial on coplanar force systems. It's going to give you some practice actually drawing free body diagrams in the actual software, which can be a little bit confusing. So let's look at, for example, the example that we have here. So we're told that we have, as shown, a crate with weight W here. It's hanging from a support rope that's tied to two other ropes at point C. So we have a knot here. And the two ropes are attached to tie downs mounted on the ceiling at points A and B. And we want to draw the free body diagram of C by drawing the forces that act upon it. So we're looking here at this knot, and we're curious, can we draw a free body diagram? So the way that this software works is you hit on the plus element to add an additional drawing component to your free body diagram. So if you think about what is going on, and I'm going to kind of go to my DocCam just to show you here. We're going to do this type of decomposition analysis a lot more as we move on in the course. But basically, if you recall, you have an actual block that has a weight. It's supported by a cable. I want to make sure that I'm using the correct terminology here. That is C, and this is A, and this is B. A, B, C. So really, what's going on is you have the actual crate itself, and it has a center of gravity, and assuming that it's symmetrical, it's right here at the middle, and it has a weight. And if this entire system isn't moving, what must be happening is this portion, this cable, which is kind of this small section here, it exerts a force on the crate, which is equal and opposite in the vertical direction. So if you notice both of those individual forces, their lines of actions pass through the center of gravity, which means you can use a particle model. You have the weight of the crate in the downward direction, and that's counterbalanced by the tension in this cable here, which is pulling this actual crate up. So in addition, what they're trying to do here is to actually draw a free body diagram in point C. So if you think about what's going on at point C, this cable, right, even though when we depicted the force that the cable exerts on the actual crate in this case, it was pulling the crate up. From the perspective of the knot at C, this cable is actually pulling this knot down. However, we know from our actual analysis that we did earlier in this chapter, saying that the actual tension in a cable has to be constant at each point, that this is nothing more than the tension in this portion of the rope, but it's equal to the actual weight. And what kind of counterbalances the downward force associated with the tension in this cable, which we know is equal to the weight from this portion of the free body diagram, that's pulling this knot down? Well, in addition, we will have a tension in the rope segments from A to C and from B to C that is pulling it up. So how would we actually direct these? Well, if you think about it, if you have this cable section from C to B, right, it can only be in tension. And what that means is that the knot is actually pulling the cable down to the left. So by Newton's third law, this cable is pulling the knot up to the right. So we know that this is directed along the line of action of CB. So you can call this TCB. And in a similar fashion, you have TAB as well. And I don't want to do the problem for you. From the geometry that you're given up here on the ceiling, you can actually determine the geometry of these two forces. However, the big picture of what's going on is that the tension in these two cables is serving to counterbalance the weight. Both of them have a vertical component, which offsets the vertical component of the weight. Cable CB pulls to the right. That's counterbalanced by the tension in cable AB pulling to the left. So take a few minutes before we get to Thursday's lecture and make sure that you can kind of work with the process of drawing free body diagrams in MyLab. Should be pretty straightforward, but it's a little bit harder than just drawing them by hand. But the advantage is you'll get your feedback right away. So hopefully this was a informative first lecture for you, and I will see you again on Thursday.